One thing which is making my life slightly difficult is that you are also doing data science 2 this semester. As per the actual sequencing, data science 2 should happen after data science 1. Okay, so the problem is that I can go into a little more details. I mean, I can bring in terms which normally you would not have heard about. But since you're already doing data science 2, you might already be familiar with those. In one sense, it is difficult because it makes my sequencing difficult, because before I talk about something, you already know something about it. Like, so you might have some half knowledge, which may or may not be helpful. But the advantage is maybe some portions I can go faster or skip. Okay, so it's like a mixed thing. So I'm finding, like, examples, today's topics, some of it you might have already seen in data science 2. So we will see. What are you doing in data science 2? You're familiar with things like expectation and all that? Are you familiar with expectation?
No, sir.
You have not never heard of it, or it was not covered?
Not heard of it.
Random variables you must have studied, right?
Yes, sir.
Distributions have you studied? Discrete
Yes, sir.
probability distributions, continuous probability distributions. So you're aware of normal distribution or Poisson distribution and all that. You're familiar with those kind of things?
Yes, sir.
Yes, sir.
Yeah, but you have not studied expectation.
Sir, in our class assignment, we just once came across to that term expectation, but formally it is not
In
covered.
what?
Sir, in our one of assignments of data science 2, we just came across
Uh-huh.
that term expectation, but it is not formally covered in class.
Okay. Is that going to come soon? Do you know?
Sir, I have no idea about it, if it is going to be covered or not.
No, I'm sure it will be covered. It is like, okay. So I'm going to touch upon a little bit of expectation, although I'm also I have not formally defined it in today's lecture, because I thought you might already know it. But again, I will maybe in the next few lectures I might touch upon it. We'll see, because my sequencing is also not very linear. I mean, I'm doing things. I'm of the lab. No, I'm trying to keep in sync with the lab. So I have to give you something which will help you to do the lab. So that is why. Okay, let's see how it goes. Fine. So let me share my screen and. Hmm. Okay, so today's talk is, I'm going to touch upon a little bit of some ideas from statistics, which we will need. Uh, we will see how it goes. Okay, so I'm not going. I'm not going to show much Python code or anything today, but I might show it in the coming lectures. Uh, uh, okay, so this part of these slides, I usually make my slides in this OpenOffice, LibreOffice. But some of these slides today, because I have to show some equations, I've done it using LaTeX. This is LaTeX here, which I've done it here. How many of you are familiar with LaTeX? How many of you have heard of it?
Only
Anybody has
heard
heard
about
of
it.
LaTeX? Sorry?
Sir, we all have heard about it.
You have heard about it. Okay.
Yes, sir.
Yeah, so LaTeX is a document typesetting system. And who made it? Do you know? So if you know
No, sir.
a little bit of HTML, if you use HTML is that hypertext markup language too, by which you can make web pages. So in some sense, LaTeX is similar to that. You write, if you want to write something, you write the source code, which is like LaTeX has its own set of rules of how to write it, and you tell LaTeX how you want it to be displayed. No, you tell LaTeX what you want to be displayed. Okay, but LaTeX will figure out how to display it. That is the nice thing about LaTeX. It is developed by Donald Knuth, who who is currently an emeritus professor at Stanford computer science. He is like a legend in computer science. He is the father of the analysis of algorithms. So that is his contribution. I mean, so he rigorously introduced how to analyze algorithms in a very rigorous manner. So the underlying mathematics and how to apply them to various types of algorithms, all that work to a large extent started with Knuth's work, and he is also the author of a series of textbooks called The Art of Computer Programming. So it is supposed to be 7 volumes, but I think only 3 or 4 volumes have come out so far. He's still writing them, and he took leave from. He resigned from Stanford to write these books. They're slightly difficult to read. I mean, we have some in our library. They are very little, quite mathematical, and it's a bit difficult to read, but it is considered like a classic. Okay. And I think volume 4 has come out, and he still has 3 or 4 volumes yet to go. He's in his 80s. He's quite senior now. And in fact, Knuth is also. I mean, he developed LaTeX. He developed LaTeX to write those books because he did not find a good enough typesetting system for the mathematics books. So he developed it. And in fact, one funny thing is, Knuth's books, what are the art of computer programming books, whenever somebody spots a mistake, he can write an email, or Knuth doesn't look at email. He reads only mail, like you have to send it to him, only then he will accept it. I mean, he doesn't check email. He doesn't have email. So if you send him a letter saying that you have found an error, and if that error is actually there, he will send you some money. He'll send you a check, but like a check from his bank account. But those checks are so famous that it's such a privilege to get that check that people don't cash those checks. People frame them. So if you go to some people who have spotted errors in his books, you might see the check from Knuth framed and kept in their office or in their house. So that is about Don Knuth. You can check out his website. Just Google for Don Knuth, and a lot of information is there on his website. Okay, so these slides that I've partially made LaTeX, so I've done it. So LaTeX produces a SVG document, like a PDF, and then I've taken a screenshot and pasted them into these slides. Let's see. So today we will talk about statistics. So I'm not talking about the statistics, the science of statistics. I'm talking about the measures of statistics. So, statistics can be used to summarize a data set. Okay, so statistics are quantities whose values are determined by the data. So if you have some data, you want to compute statistics on that data. So those statistics are, like, for example, sample mean, sample median, sample mode. They are all of statistics. Okay, so I repeat, I'm not talking about the science of statistics. I'm talking about the measures called statistics. Okay, so for example, sample median and sample mode are statistics which indicate the center of the data set, like the center of mass, you can say, where most of the data lie, or where. So the center of mass of a system or of a body is where most of its mass is concentrated. So similarly, the center of a data set, or the center of data, is essentially represented by the statistics of mean, sample median, and sample mode. There are other statistics, for example, sample standard and sample correlation. Okay, we'll look at all of them today quickly. Again, I'm not going into details, but some formulas, etc., we will show. And again, to study this in depth, you will need background in random variables and a background in probability. So that is like actually beyond the scope of this course, but little bit I'll try to cover, especially with some Python-based stuff, which you can actually see some of this. But most of it, I'm hoping that you will study in data science too. Okay. So you must have already heard of mean, median, and mode, and standard deviation correlation, right? But here I've told you this is sample mean and sample median and sample mode. So why did I put the word sample in front of all this? In other words, what is the difference between mean and sample mean? Can somebody guess? Did you understand my question?
Yes, sir.
What is the difference between mean and sample mean? What is a sample, by the way? What is a sample?
The set of data that we are having.
No, can you be a little more precise? Set of data, yeah, in all sense, everything is data, but okay, can you relate a sample with a population? What do you mean by a population, and what do you mean by sample?
Sir, sample means getting only few of the, data,
Yeah,
collecting only
yeah,
few
that is
data
right.
of the.
Sample, yes, sample is actually a subset of the population. Sample is a subset of the population, because you may not be able to access the entire population. It just may not be logistically possible. You might have the difficulties. No, even the census data which we take, although government officials try to visit all houses, it doesn't mean that they have visited every one of the single population in India. I'm talking about just India. Okay, like our estimate that India has like 1.2 billion is again an estimate. We really don't know how many people are there in India. It is not possible to find out exactly the exact number. Is maybe it's possible, but it's very difficult, and it's probably very expensive and not worth anybody's time. So we go by estimates. And even in that, even when you do a big exercise like finding out census and all that, you are essentially targeting only a sample of the population. It may be a fairly large sample, but still it is not, uh, it does not cover the entire population. So the population here doesn't mean population of people. In maybe in terms of census, yes it is, but in general, in the science of statistics, population is the whole of the data, the universal data, which is there somewhere. And by drawing samples from this population, we are trying to estimate some ideas about the population, because we cannot work with the entire population. Okay, now for example, in COVID also, uh, maybe if you look at all the people who have got COVID, that is your population. But now to do the study the effectiveness of a vaccine, you cannot go and check the effect of the vaccine for all the people who have got COVID. Although even if all of them have got the vaccine, even then it is not possible for you to go and monitor how all of them respond to the vaccine. You have to do it with a small sample. Okay, so population here can mean like let's say if you're tracking the number of tigers in India, population could mean the population of tigers. Population could mean now for example, generally in statistics, population means any type of data, not necessarily people. And so sample is a subset of that. So when I sample mean, that means I have some population from which I have drawn a sample. A sample here means a subset. So a sample could have hundreds of entries. And the mean of that sample, the mean of that 100 data points is what we are calling a sample mean. But what is the true mean? What is mean? Mean means the true mean. The true mean is the mean of the population, which we have no way of estimating. So sample mean can be considered as an estimate of true mean, but there's a catch. What is the catch? The sample mean is an estimate of the true mean, but with a catch. What is the catch?
Sir, it depends whether the entire population has same properties or something like that.
No, we are not considering the entire population. We are considering only a sample because we don't have resources to go and take data from the entire population. So entire population is ruled out. Now, for example, if I don't know if is there anybody from Bombay here? Now, if you go to Bombay and if you see the local trains, for example, now suppose you want to know the ridership of the age of the riders who take the Bombay Metro. I mean the Bombay locals. Okay, so now what will happen? So your target is to find out what is the range of people the range of age of the people who ride on the Bombay local trains. Okay, so now if you go to some big station, Dadar or something, you go there, and then suppose you start at let's say 5 p.m. and finish at 7 p.m. 5 to 7 p.m. If you sample the ages of people riding in the metro during, I mean, the locals at that time, 5 to 7, you will, and if you take that as your sample, you will finally conclude that the ridership of the Bombay locals is mostly people between let's say ages of 20 and ages of 60. Okay, why? Because that is the maximum time when most of the office people come out from the office. And so take sample there at that time, then that sample which you're taking is actually a wrong sample. It is a biased sample. It is not a good sample. So if you are going to use your sample mean as an estimate for the true mean, you should do your sampling properly. So this exercise which I told you, taking the ages of people between 5 and 7 p.m. in Bombay local is not a good sample because that is not covering the samples at the other times of the day. So there may be a lot of school students using it. There may be a lot of other people, old retired people also may be using it during midday to avoid the crowds. So actually the ridership may be from as old as 10 years to 95 years. But because of your wrong sampling, you are concluding that the average age of the mean of the population using the Bombay local is, let's say, some 35 years, which is wrong. Okay, so it depends on how good your sample is. So how to do sampling is a different exercise. So statisticians and other experimental psychologists and others spend a lot of time to an experiment which will collect the right sample. So just remember that sample mean is an estimate of the true mean if and only if sampling is correct. If the sampling is wrong, the sample mean will not really reflect the true mean. Okay, and how do you find the true mean? One is of course go to the entire population, but if you know something about random variables and about distributions, then the mean can be found out by using the probability distribution of that random variable. That maybe we'll see later at some other time, but you might have already seen it in data science too. We'll see. Okay, so what does sample mean? So here, when I talk about whenever we have a sample, we know that it is a finite sample. So there are data points x1 to xn. So this is done in LaTeX, for example. This part of the slide is done in LaTeX that you can see, and this is actually the open office font. This is the LaTeX default font. Anyway, so data points, we are for this lecture we are considering the data points x1 to xn, and we are also assuming that here all the data points are scalar values. For example, age is a scalar value. Okay, so single numbers, it could be floating point, it could be integer, that doesn't matter, but we are looking at scalars. And the sample mean here is defined as this is the sample mean. This formula you know already, all of you know, it is just the sum divided by the total number, and you represent it usually as x bar. Okay, so this is the sample mean. And there are several properties are there of the mean. One simple property is that if you transform the data by adding a constant to it, mean also gets shifted by the same constant. Right? This you can actually prove. It's just 2-3 lines. You can prove that. Now let's look at example. This is from statistics textbook. So now these are motorcycle accidents in the year 1976 in the US somewhere, I think. So I've got a classification of the accident. Okay, and we are concentrating on head injuries. Okay, now and so we are going to look at two populations, or let's say two samples. Uh, uh, One is a sample of the population who is wearing a helmet, and the other is the sample of the population who not wearing a helmet. Right? And so we classify the accident in various levels. 0 means there is no head injury. 1 means there is minor head injury. Then 2 is moderate, and so on. Whereas 6 is fatal. Okay, so as the classification index, let's say we'll call this column here as classification index. As it becomes greater and greater, the more severe is your injury. Fine, and this is what it means. And this is our data. Our data is here. So there are two columns, with helmet and without helmet, and these are the number of people in the population who had this type of injury. Okay, so that was 248 people had who were wearing helmet, for example. 248 of them had no head injury. 58 had minor head injury, and so on. Okay, so now you want to, let's say, see what is the severity of a motorcycle accident wearing a helmet versus when you're not wearing a helmet. So I repeat, we are interested in finding out what is the severity of a motorcycle accident when you're wearing a helmet and when you're not wearing a helmet. Okay, so what is it that we want to predict? We're not actually predicting. We are coming up with a number which generally says what is the severity of that accident. Okay, but what are we trying to predict? What are we trying to understand here? I mean, what will give us the data which we want? Which so suppose you consider this table. We are trying to find out the measure of this particular column. We want to find out what is the severity of the error of the injury. Okay, so that's why I'm saying I'm constrained by the terminology here, because if you I'll come to that in a minute. Okay, so maybe rather than asking you this question, let me tell you what I want. That may be easier. So now what I do, let's find out the sample mean. Okay, let's find out the sample mean. So this is actually a frequency table, right? This table is giving me the frequency table for each of these categories. So let's find out the sample mean. So here actually I'm doing the weighted sample mean, because if I have my data in terms of frequencies, the sample mean is actually the weighted sample mean. I'm weighing it by what I'm trying to determine. The mean of what I'm trying to determine, that I'm using as a weight. So basically I'm doing it. So 0 into 248 plus 1 into 158. So I'm just multiplying. I'm multiplying this number with this number. This number with this number. It might seem a little strange. That is basically what we're doing. Finding out a weighted average. Okay, rather than just finding a normal average here, we are finding out a weighted average. And this is giving me 0.432. And for non-helmeted rider, this is giving me 0.902. Fine. So now, so if I can interpret this as this is the mean of the head injury severity. I mean, like, so we know that the higher the severity severity index, the more serious is the injury, right? So if you interpret it in that way, this basically means that when you're wearing a helmet, the severity is 0.4, and when you're not wearing a helmet, the severity is 0.9. Okay, so essentially what means is you will get you are more likely to have more serious injury when you're not wearing a helmet versus when you are not wearing a helmet. Okay, so from this data, it is indicated that the idea is that the suffering which the riders underwent is more when you don't have a helmet versus when you have a helmet, because the classification index here, the more is that number, the higher is the suffering. Actually, so this can be related to what this is what I was asking you. This is what is in some sense giving you what is the expected value. So what is the expected suffering from this data? What is the expected suffering from this data? So the expected suffering without a helmet is 0.9, and the expected suffering with the helmet is 0.4. Okay, so this is somewhat related to this is the idea of the expectation. The expectation is giving you what is the expected value. For example, in some population sample, if you randomly choose some value, and what is the value that you're going to get, that is giving you the expected value. So the is actually an operator, is actually an operation which you do. So you have to multiply the observation with its probability distribution, and if you do it over minus infinity to plus infinity, it will give you the expected value. Minus infinity to plus infinity x p of x, where p of x dx, where p of x is the distribution of x. Okay, I mean, I'm talking about a continuous case. In the discrete case, it is a summation. Anyway, that we will cover maybe later. But so the thing is, we are finding out the expected suffering here. That is what I wanted to tell you. Okay. Because these numbers are small, it's not that we are getting these numbers close to 5 or 3 or 4. These numbers are small because you see, most of the time, whenever there is an injury in the of the person, most of the time it is not they are not having any injury. So statistically, most of the suffering, when you compare this suffering with this classification index, these are very small. These are actually less than 1. These are actually less than 1. That is because most of the time, whenever somebody has an injury, most of the time he or she escapes without any injury. Okay. If you want to ask if the motorbike is a safe means of transport, by looking at this data, you can say yes, probably motorbike is a safe means of transport, because most of the time the expected suffering score is less than 1, whether or not you are wearing a helmet. Is the idea of expectation clear? We have not defined it formally, but this is what we are doing. The expected value is it is basically a weighted average of the samples. Okay, let me go ahead. Then there are deviations. You have mean, which is giving you the center of mass of where most of the data lies, but data is expected to deviate from it, and that deviation is done by the you can find out the deviation by subtracting each value from the mean. And okay, there is one homework for you. You can prove that xi minus x bar is equal to 0. So that means the sum of total deviations is going to be 0. Okay, for any data set. So this is the deviation. We will come back to it in a minute. Another measure another statistic which we have seen is sample median. We have seen this already. We have seen Python code also for this. So here we order the values of the data from smallest to the largest. If the number of samples is odd, then it will be the middle value. Median is the middle value. But if the number of points are even, then sample median, here I have defined it as the average of the two middle values. Okay, some books take one of the middle values, but you can also take the average. Only thing is, if you take the average, your median will be a number which may not be present in the data. That's okay. And we also saw earlier that sample mean is affected by extreme values or outliers, whereas that is not the case with the sample median, because median is more robust to outliers. So when do we use mean and when do we use median? See, I'm talking too much. Do you guys have any questions so far? No questions? I don't know how many of you are there.
So,
Hmm.
so,
Yeah.
so for the previous case, can we like first normalize the data out of one and then plot the like mass functions to check the uh, severity?
No, normalization is not a good idea. Normalization is not a good idea. What will you normalize? What do you want to normalize? See, we are trying to find out the expected severity. So we want something which makes sense for us, because we have a index for severity which is from 0 to 6. So we would like to get a value within that range. So if you normalize, I mean, so what did you say you want to normalize? You want to normalize the frequency or you want to normalize the index?
So the frequency.
That may not change the answer, because basically that rather than dividing by 31, you will be dividing by, oh, actually I made a mistake. For non-helmeted, it should be 439. Actually, if you, so rather than dividing by 331, you will not be dividing it because the sum will be 1. So that will not change the answer. So the expected value should be in the range which we are expecting the value. Like if you have values between 0 and 6, when you take the expected value, we would like to get the value between 0 and 6, because that is what is making sense to us. So we don't want to change the range of the data. So normalization here may not be the right idea. Okay, that you will understand only when you do that. If that is not clear, let's wait for some more time. Maybe in your data science 2 it will get covered in more detail, but maybe later lectures I might touch upon it once again. Okay, so normalizing doesn't make sense. That's what I'm trying to say. Anything else? Okay, let's go. We are already almost 8:40. So we are talking about, like I said, sample median, right? So you know the difference between mean and median. So now when we use what? When do you want to use mean and when do you want to use median? For example, I'll give you an example. Now, suppose in a city you want to apply some income tax rule. You're going to have a rate of income tax rule. Okay, so how much income should the city expect? So there are cities. There in a city there are, let's say, a lot of people. Some people pay very less tax. Some people pay very high tax. Now you're going to apply one uniform tax structure to all of them. And how much income do you want to expect? So here in this case, will you use mean or will you use median? Yeah, it is probably good to use mean here, because there may be very rich people who have a lot of money, who may be, and there may be very poor people who have very less money, who might be struggling to pay tax. You want to keep, since all of them are going to be taxed at the same amount, you want to put something which is reasonable, which takes into account the smallest values as well as the highest values. So in that sense, the outliers here are useful. So in this case, maybe mean is better. On the other hand, if building some middle class housing, okay, and you want to know how many people will be applying for this housing. So in some city, or the government is going to build some housing for middle class people, and they want to know roughly how many people might be applying for this. In this case, it is better to use median, because there may be some outliers. There may be some people, because there because presence of a few people, you don't want to create large number of houses. Like for example, if you take a mean here, because of some outliers, you might finally get, because outliers affect the value of the mean, you might end up building a lot of houses which may not be occupied, because there are actually many people who want middle class housing. So these are two examples of when to use what. So that really depends on what is the application which you are looking at. If you want the effect of outliers, you go for mean. If you don't want the outliers, go for median. But typically, when you're analyzing some data, it is good to have an idea of both. Okay, so these are useful statistics. Another third statistic is mode. Mode is the most frequently occurring value. For example, in this data set, sample mode is 10, because mode 10 has appeared the maximum number of times. So we'll come back to the deviation. So for these two sets of data, A and B, have the same sample mean, but B is more spread out than A, right? So to measure this thing, you have to measure the variation from the mean. And one of the way, because see, one of the ways to do that is by finding out the this variation. So why okay, this variation, why are we using square here? Why don't we just use xi minus x bar?
So that was
The value could be negative.
so that yes.
Yeah, we want to, okay, now if you see, I think I've, so this one here, this is already showing me that the sum is going to be 0. The deviations from both sides are going to be 0. So if I do it like that, then the positive deviations will cancel out the deviations, and again I get 0. So to avoid that, we want we'll take the square, so that the deviation is always positive. Okay, we can also take the absolute value, but this is more convenient. And so this is how you define sample variance. So sample variance is how much is the variation from the mean of a data set. And you might notice that it is divided by n minus 1 rather than n, whereas in mean we used n, whereas in variance we use n minus 1. That is because n minus 1 gives you an unbiased estimate. So if you divide it by n, there is a chance that the variance is biased by some is a biased value. So generally we take the unbiased estimate. That requires some more derivations that we'll not see here. Okay, so just remember, variance divided by n minus 1 will give you the unbiased estimate. This is basically a bias variance trade-off. I think if you, maybe in data science 3 you might learn that, or if you take a pattern recognition course, there is a deviation between, there is a trade-off between how much bias you want versus how much variation you want. Okay, so too much variation means your bias will become very low, and too much bias means your variance will become very high. So generally sample variance, since we are taking the square, it is generally denoted as s square, which is sample variance, and the positive square root of that is known as the standard deviation. So both those measures are useful. That we'll see in a bit. Then we'll talk a little bit about a data set which is normal. A normal data set is one whose histogram, it looks like this. It is highest at the value. It is bell shaped. That means both sides it is kind of symmetric, and it decays from the middle. Okay, so bell shape is for the continuous case, but so the histogram, what is the histogram approximating? So if you're taking a data set, and if that sample is good, if you're taking some sample, and if you're plotting its histogram, and if the sample is a good sample, That means it models accurately the population. What does the histogram approximate?
Sir, the distribution of the data.
Yeah, the histogram approximates the probability distribution of the data. The histogram approximates the distribution. Okay, so if the sample is good, a quick way to find out how the sample or how the data set, how the data behaves is by plotting its histogram, which will give you the approximate shape of the probability distribution of the underlying sample, of the underlying population. So this is normal data. Of course, there are some variations. The data could be approximately normal, or data could be skewed. So this is an example of a skewed data. The histogram here is skewed. No, it is skewed towards higher values. So it is skewed towards the right of the mean. Okay, the most of the mass is along higher value, higher than the mean. Most of the mass of the data is higher. The mean is not symmetric. So if the data is normal, there is an empirical rule which basically relates the mean and the standard deviation. So the data is approximately normal. Approximately 68% of the data lie between the mean and one measure of the standard deviation from either side. Plus minus s is the standard deviation, the positive square root of the variance. Approximately 95% of the data lie between two standard deviations, and 19.7, almost all the data lie between three standard deviations. This is for normal data, if the data is normal. Fine, just keep this numbers in mind. We can use them in some problems later. That's okay. Sometimes data in like normal distribution is very nice in theory. Okay, and many biological populations or many natural populations follow approximately normal. But many of them, when there are, let's say, two distinct subpopulations, when there are two distinct subpopulations, each of which could be normal, you might not actually get a normal distribution, but you might get a superposition of normal distribution. That is what is shown here. So let's say, for example, in a gym, for example, a club or a gym, you want to measure the weights of the people who use that gym. Okay, so if you collect a good sample, you will not get a normal distribution. Actually, you will get a distribution like this, which is actually a bimodal distribution. Bimodal means there are two peaks. Why is there two peaks? There are actually two subpopulations here. There is a population of men and a population of women whose average weights differ slightly. So because of that, you will not get a single normal distribution. You'll actually get two distinct peaks corresponding to the two subpopulations. Fine. So this is bimodal data. So many real world data usually have multiple modes. There are multiple peaks in the data. All of them may be normal by themselves, but when you take it as a whole, if the different populations are distinct enough, you will get different peaks in the distribution. So in probability theory, this is modeled by what known as mixture models. So there is a mixture model which will model this kind of data. No? Gaussian mixture model. You might have heard of a Gaussian mixture model, which is a distribution, it's a mixture of linear combination of some Gaussian distributions. And this kind of data is unimodal. This is unimodal because there is only one peak. But here this is bimodal data. Another statistic which we are interested in is sample correlation coefficient. This we should look at the association between pairs of data x and y. Okay, so how does increase in x increase the effect of how does an increase in affect y? That is, now for example, this data here is a sample which shows the number of cigarettes a person is smoking in a day with the number of free radicals in the person's lungs. So having free radicals, more free radicals in your lungs is not a good idea because they are more reactive. So if you plot it as a scatter, you can see that as the number of cigarettes smoked increase, the number of free radicals also increase. So as if you call this one as X and this one as Y, as X increases, Y also is increasing. So there is a distinct relationship between X and Y. And now this is another example of the number of, this is a sample of only 10 people. There are only 10 samples here. Sample of is 10 basically. So this is giving you the number of years a person spends in school versus the number of the pulse rate, that is the heart rate of that person. Okay. So now if you plot a scatter diagram of this, so like I said, whenever you have binary data, you want to see some association between them, you can always use a scatter plot. So if you do the scatter plot here, you can see that as the number of years in school increase, the pulse rate of the person becomes lesser. So in general, lesser pulse rate generally means a more healthier heart. So this seems to mean that there is some relationship between the number of years spent in school versus the number is their average pulse rate. This seems to decrease. No? So this kind of thing is captured by the correlation. So so if you consider, see there are two values here. There is an X and a Y, right? There is an X and a Y. So X will have a deviation, X will have its own mean, Y will have its own mean. So you can now measure the deviation of X from its mean. You can also measure the deviation of Y from its mean. That's what we are doing here. We are finding out the deviation of X from its mean, deviation of Y from its mean, and you're taking its product. Okay, and generally, if the deviation of X from its mean is also resulting in a deviation of from its mean, a large deviation of X is also resulting in a large deviation of Y with the same sign, then you will see that generally as X increases, Y increases, or X decreases, Y decreases. So to normalize this and to get a proper measure, what we do is you find out this product over all the samples. You divide it by n minus 1 to normalize it. And since these are products, you just divide by, because this is basically giving you the standard deviation of X, this is giving you the standard deviation of Y, you divide it by the product of the two sample deviations. So that is what you're doing here. So this is, you find out the
Not audible. Sir,
product will
sir,
generally,
you are not audible.
am I audible now?
Yes,
Yes,
sir.
sir.
Now,
Now you are audible.
Okay. Where did you lose track? Did you understand about what I said about we are normalizing by the two standard deviations? So this variation is normalized by its standard deviation. This is because this is essentially the standard deviation, right? X minus X bar is nothing but the square root of X minus X bar, the whole square, which is the variance. So this is the standard deviation. This standard deviation, you are dividing it by its own standard deviation. So you will get a value close to 1. Similarly, this standard deviation, you are dividing by its standard deviation. So this also will give you a value close to 1. And you're normalizing it for the whole data. And so essentially you will get this Rxy, which is known as the correlation coefficient. And correlation coefficient, because of the way we are doing it, it has a value between -1 and 1. Fine. So that is that gives you an idea of correlation. So if the two variables are X and Y are directly correlated, the correlation will be 1. That is a straight correlation between X and Y. The correlation coefficient will be 1 or -1. But if there is less correlation, then the value will be between -1 and +1. Zero correlation means there is no correlation between X and Y. Okay. I'll skip this part. Let's not into this now because we don't have time, and maybe we'll come to it later in some other lecture. But what I wanted to tell you, the essence of today's talk is this: the last slide. Okay, correlation measures association, not causation. This is very, very important because as data scientists, if you measure correlation, you cannot say it is the cause of something. For example, see in the previous data what we saw strong negative correlation between. So if you see this plot here, this was a line with a slope which is having a negative slope. So the correlation here is negative. Okay, is somewhere between 0 and -1. So this seems to mean that there is a strong negative correlation between number of years in school and the resting pulse rate. Okay, so from this data, do you conclude that if you spend more time in school, your pulse rate will be lesser? We are looking at causation now. Cause means there is a cause and effect. So if the is the cause of less pulse rate due to spending more time in school, more years in school? Does spending more time in school give you lesser pulse rate? So you have to be careful there, because usually correlation, having strong correlation between two variables, does not mean causation. That does not mean that one variable causes the other. Okay, association. Association is not causation. And for example, it might be, there may be other factors. For example, if you spend more time in school, you might get a better job. You might, and job gives you more time to do things like exercise. So directly spending more time in school is directly not going to give you a reduced pulse rate. Okay, another example, a lot of examples. Now, the faster a windmill rotates, more wind is observed. Therefore, windmills cause winds. Okay, this is another statement, because you're seeing a windmill, it's going very fast, and there's also a lot of wind. So if you measure the correlation between wind speed and the RPM of the windmill, you'll see a very positive correlation. But you, as a person of the world, you know that windmills do not cause wind. In fact, it is the other way around. Because of high wind, there is windmill is rotating. Okay, but in some data analysis, if you're having some strong correlation between uh, two types of data, you cannot assume that this one is causing this. Fine. So correlation measures only association. You cannot say that because of correlation something is causing the other thing. Some more examples. Children that watch a lot of TV are violent, therefore TV makes children more violent. Need not be, right? Another example, sleeping with shoes is strongly correlated with waking up with a headache. Therefore, sleeping with one shoe is causing a headache. That is again no correlation, because actually there could be some other missing factor. For example, if you have a lot of drinks and go to bed with your shoes on, next day you'll get a hangover, and that hangover is going to cause you the headache. It is not because of you wore the shoes and went to sleep. As ice cream sales increase, the rate of drowning deaths increases sharply. Therefore, ice cream consumption causes drowning. There is also these are false causations, because there could be some other missing factor here. For example, the summer weather. In summer, a lot of people eat a lot of ice cream. In summer, people go for swimming, and because of that, because people go for swimming in summer, they might drown. So it is not, the ice cream has nothing to do with drowning. So just remember, correlation measures association. It is not causation. Correlation between two variables does not indicate one causes the other. Okay, I will stop here. And
Just one question, that for
yeah,
the final statement, can we say that the summer weather directly causes more drowning deaths?
summer
Like the
weather.
missing.
Yeah. So you're saying some weather in summer is causing more deaths. Can you conclude that?
Yes, sir.
Again, there may be other factors. See, this is where you, as a data scientist, if you only look at the data, you might make erroneous conclusions. So to do it properly, you need to have some knowledge of the underlying system. What is the underlying domain? I mean, like, you need to have additional knowledge. Just from data, you cannot conclude that. Even that we might be tempted to say that high temperatures in summer will cause more drowning, but there may be some other hidden factors also. It may be, suppose it is a population of students who already learned swimming in school, so such people are less likely to drown. But if it is a population of kids who have never learned swimming and in hot summer weather they have gone for swimming, then there is a higher chance that it might drown. So there may be other hidden factors here. So you have to be careful, so that it is not necessary that summer weather causes more drowning. No, it really depends on the type of type of data you have sampled and the type of the underlying population. So again, there are complex. There may be many more factors here. Okay, unless you know that
But
it's a
we
very
can
controlled
say
experiment and you
that
know that.
summer
Yeah,
weather is we can say that summer
I can't
weather
hear
is
you.
associated with ground events. Am I audible
Yeah,
now,
we can
sir?
always say there's some correlation between summer weather and yeah. You can say that there is some correlation between summer weather and drowning, but does summer weather cause drowning? That you cannot really answer. I mean, like, unless you know what type of data is collected, you cannot answer that.
Okay, sir.
Okay, an increase in GDP does not necessarily. I mean, an increase in GDP may be positively correlated with the performance of the stock exchange. But GDP and stock exchange maybe relate. Maybe there may be other factors. Political factors may be there. There may be other, the export deficit, the import deficit, the corona crisis. All those things might also be playing a role. So we just cannot. Uh, we just cannot. So we can only say that there is some correlation, but we cannot say there is a causation. Okay, it is already 9:01. I'll stop. I'll upload the slides.
So in the
That
just
the previous slide I will.
so
Yeah.
in just one example that children that watch a lot of TV are violent, then therefore TV
Mm,
makes children more violent. Why it could be false?
mm.
Means
No, it is.
I
It
can't
is. It
relate.
could be. No, it is not necessary that watching TV is going to make you violent. I mean, so if you conclude by the positive, I mean, like, by seeing the positive correlation between violent children and children and the children who watch TV, if you say that they are positively correlated, it does not necessarily mean that TV is causing the children to be violent. If the child is already violent, for example, maybe the child has undergone some social trauma, or maybe some abuse or something at home or wherever, or it might have had a broken home, or due to some reason the child is already violent, that it might be that the violent child is watching a lot of TV in some home or something. I mean, like, so this is just an example. So what I'm trying to say is there may be many other factors which we have to consider, which may not be reflected in your data. Your data cannot capture everything. You can only collect what is available to you, what you are able to sample properly. But there may be more underlying complex phenomena which may not be numerically capturable, and so you have to be careful.
Okay, sir. Thank you, sir.
Sir, what is the timing of extra class?
No, today there is no extra class. There is no extra class today. No extra class. There will be a
Okay.
quiz Tuesday. I'll send out an email later today. Okay. Okay, I'm stopping. You are already late for your next class. Thank you, and see you on
Thank you, sir.
Tuesday.